Welcome to Spring LIB.
Okay, we need to make the following ketone through acid-catalyzed hydration of an alkyne. Now recall, if we have an alkyne, which one side has a methyl group or an alkyl chain and the other side has a hydrogen, and it undergoes acid-catalyzed hydration, it will form an enol, but in particular it'll form an enol where the OH ends up on the more substituted side of the alkyne, in this case the red carbon, like so. Right, this would be the red carbon, and this would be the blue carbon. And that this then would tautomerize into the following ketone. So then that means that what we'd like to do is to turn an alkyne into an enol, in which we have a 6-carbon chain, and we end up either with a double bond between carbon 2 and 3 and a OH on carbon 3, or a double bond between carbon 3 and 4 with our OH on carbon 3. Right. This would be either of these. If we could get these in high yield, would tautomerize to the ketone that we're after. Okay, so let's look at our options. Option 1 is the following alkyne. Now this is a 1, 2, 3, 4, 5, 6, 7 carbon chain, so that's certainly not going to work. We need a 6-carbon chain, so this one's off. Option 2. We have here a 6-carbon chain, so that's doing much better. And the possible alkene or enol products of this would be that we end up with a 1, 2, 3, 4, 5, 6 double bond between carbons 3 and 4, like so. And then sides 3 and 4 are basically equivalent as to which side of this double bond would end up with the OH. That is, if we put the OH here, that's exactly the same as putting the OH here and simply flipping the molecule around, which means no matter which enol forms from this alkyne, we're going to get this enol, which we know can tautomerize into the ketone we're after. That is to say, because of the symmetry of this molecule, there's really only one possible enol that can form, and that enol goes directly to the ketone that we want. If we explore our other options, we'll see that's not always the case. We see that the third option is a terminal alkyne, which can't even possibly get us to either of these, right? We can only end up with a double bond between carbons. This will give us an enol that looks like this, right? Which doesn't match either of the enols we're trying to make. We need a double bond between carbons 2 and 3 or between carbons 3 and 4. So a double bond between carbons 1 and 2 won't help us. And if we look at our final option, it can be catalyzed, undergo acid-catalyzed hydrolysis into an enol with a double bond between carbons 2 and 3, which is good. But from there, we'll notice that the OH can either end up on carbon 2 or it could end up on carbon 3. And only one of those, when the OH ends up on carbon 3, tautomerizes to the ketone we're after. Right? So this is, our fourth option is possible. It's just not as good as the second option. So in fact, option 2, the first one we looked at, which had the correct number of carbons in it, is the correct alkyne. And then the reason for that is that the alkyne selected is best because there's only one possible hydration product, right? That's that second reason there. Right, so in full, you'd want to check boxes 2 and 4.